Hello again. This is Math 1220 coming to you from the College of DuPage, and the title of this lecture is Graphical Solution to Small Linear Programming Problems. As always, be an active listener as you watch this video. So here we go, linear programming, the graphical method. Many problems in business, science, and economics involve finding the optimal, that is the best, value of a function. For instance, the maximum value of the profit function or the minimum value of the cost function, subject to various constraints such as transportation cost, environmental protection laws, availability of parts, and interest rates. Linear programming deals with such situations. In linear programming, the function to be optimized is called the objective function, and that's linear. And the constraints are given by linear inequalities. Linear programming problems that involve only two variables can be solved by the graphical method, which we're going to do with the following example, and then we'll talk about how we did it. So in our example, we want to find the maximum and minimum value of the objective function z equal 2x plus 5y subject to the following constraints. First thing we do is we graph all these constraints. So I graph the first function and I get this red line, and then it's less than or equal to, so I go underneath this one. The next one is also less than or equal to, and that is this one. So you see I'm taking the intersection of less than or equal to. Then I say x plus y is bigger than or equal to 1. Here's x plus y equals 1, and it's what is above. So, and then I go x is bigger than or equal to 0, and y is bigger than or equal to 0. So that forces us to be inside this region where they overlap, and this is called our feasible region. Now, we're talking about this function, and this function has values for anything I take for x and y in these feasible regions. So let me just be taking various values. So these are going to be parallel lines. So I'm drawing them. Now this one doesn't intersect the feasible region at all, but this one does intersect the feasible region, as does this one. And eventually there would be this dotted one here as well. This one goes outside, but this dotted one as well. Now observe that that means that as I've graphed the feasible region, I actually will intersect at a corner point. Now what I can do then is I can find out what all these corner points are by taking the intersection of the lines. So for example, I can take 3x plus 2y less than or equal to 6 and minus 2x plus 4y less than or equal to 8, and I can say those two intersect at this point. And I use the techniques that we talked about before to find that point. And if I do that, taking those two, I can solve this. That's what we studied previously, and I get this is 1/2 comma 9/4. The other thing I can do is I can find the intersection of the others as well, and I can find this point, this point, this point, and this point. So I find 1, 2, 3, 4, 5 points of intersection. So those are values of the corner points. So a corner point is a point in the feasible region where the boundary of two constraints cross. The feasible region is bounded because the region is enclosed by boundary lines on all sides. Linear programming problems with bounded regions always have solutions. However, if example 1 did not include this constraint, it might have been unbounded, and there would be no way to maximize the value of the objective function. We're going to use, to solve this then, the following theorem called the corner point theorem, which says If the feasible region is bounded, then the objective function has both a maximum and a minimum value, and each occurs at one or more corner points. If the feasible region is unbounded, the objective function may not have a maximum or a minimum, but if a maximum or a minimum exists, it will occur at one or more of the corner points. Now the theorem simplifies the job of finding an optimum value. First, you graph the feasible region and find all the corner points. Then you test each point in the objective function. And then you identify the corner point producing the optimum, maximum, or minimum values. So in the example that we just did, we could find that these were the 5 corner points. Now there's quite a bit of work in finding these, but you can find these 5 corner points. So then I take each of these, the value for x and the value for y, x, y, x, y, x, y, x, y, and I substitute this into my objective function. So when I put the first one in, I get 5, the second one I get 10, this one I get 49 over 4, which is a little better than 12. Let's see, here I get 4, and here I get 2. So the maximum happens here, and the minimum happens here. So that says that the solution is, the objective function is 49 over 4, and that happens when x is 1/2 and y is 9 over 4, and the minimum happens when x is 1 and y is 0, and the objective function is 2. So those are our solutions, and now we have solved one problem completely. Now this is a summary of the steps for solving a linear programming problem using the graphical method. So first, you write the objective function and all the necessary constraints. We are going to be doing some word problems, and so there's a step up here. A step 0 is reading and understanding the problem. Then we write the objective function and all the necessary constraints. Then we graph the feasible region. Then we determine the coordinates of each of the corner points. Then we find the value of the objective function at each corner point, because we know the max or the min has to occur at the corner points. Now if the feasible region is bounded, the solution is always given by the corner point producing the optimum, max, or minimum value of the objective function. If the feasible region is an unbounded region in the first quadrant and both coefficients of the objective function are positive, then the minimum value of the objective function occurs at a corner point and there is no maximum value. There is a corresponding statement also for a problem with a different objective function where the objective function has different coefficients. So if it's bounded, there's always a solution. If it's unbounded, there may or may not be. Let's look at another example. Now I'm going to go through this really pretty quickly, but what you should do is pause the video and do each of the steps. So the first step that you should do is sketch the feasible region for the following set of constraints. So here they are. So you should pause the video and sketch all of those graphs. And then we're going to find the maximum and minimum values of that. So first step is sketch all of those graphs. Now if you do, you will get these region. Then what you will do, you go through and you will solve and get the corner points. So you'll find this point where those two intersect, this point where those two intersect, this point where those two intersect, and this point where those two intersect. Then and you will take these points, and these points will end up being 3, 8, 3, 2, 6, 4, and 5, 12. And you will substitute them into the objective function. And we're doing it for the same objective function here. We substitute in and we will find that this is the minimum that happens here. It happens at 3, 2, and it's 19. And the maximum is 49, and it happens at 5, 12. So those are the answers to this problem. It takes you a lot longer to do this than it does for me to talk through it. Here's another problem for us to consider. Solve the following linear programming problem. So we're minimizing this. We want to find the minimum value of this subject to these constraints. Well, first of all, we have to graph those constraints, so you really should do that. But if we graph those constraints, this is the feasible region that we get. It is bounded, and there are going to be 3 corner points. A corner there, and a corner there. This one is 4, 2, that is 10 over 3, comma 5 over 3, and this is 0, 10. So then we're going to take those corner points and we're going to substitute them into the objective function, which this time is x plus 3y. We're going to evaluate those and we're going to take the minimum value. And the minimum value between 30, 10, and 8.33 is going to be, and actually that's not 8.33, that's 25 over 3 exactly. The 3 would continue, so the minimum value of z is 25 over 3, and it occurs at 10 over 3 comma 5 over 3. Here's another example. You want to solve the following linear programming problem. You want to minimize this objective function subject to these constraints. So if you graph these constraints, you get this. Now this is the first time that we have an unbounded region. So that means we might not have some solutions. And certainly when I look here, I see that this is always going to be bigger than or equal to 0, the objective function, so I could make it as big as I want. There's not going to be a maximum value. But still, I find what these corner points are by finding the intersection of these equations. And I find that the points are 0, 10, 2, 4, and 10, 0. So I will substitute those in to the objective function, and I find that there are 2 that yield a minimum value. And so there are alternate optimal solutions. It can be at 2, 4 or 10, 0. And either way, you will get 20 for the objective function value. I am going to ask you to turn in an LSA and do a minimization and a maximization problem in preparation for what I might ask you on a high stakes assessment. I'm going to later on tell you when these are due, because right now I don't know when we'll be getting exactly to this in class. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.